So let's go ahead and open up the sample model, and I'll walk you through what some of those ones look like. So. All right, so. All right, so let's start here. We'll sort by type. And let's start with the IMP file because that's where it all begins. So here you see header options. It's got my output. It's got what my save file is going to be. It's got the M line. I'm not even sure what that does. And then the title. And here's header operations data. They call a TD pre-build function that they define. This is a directive. That's why it can start in the column to the left. So when the preprocessor sees this, it's going to expand it. What this is saying is build all of the submodels that I've defined as my solution configuration. You could alternately say build, give it the name of the solution configuration, and then separate by commas all of the submodels that you wish to build after it. So this does allow you to include things in the Cinda model, but then not include them in the solution, or start with it in the solution and then remove it afterwards. So let's say I do a launch analysis and I drop away the fairing. So I could do the launch analysis up to the point where the fairing jettisons and then rebuild again without the fairing submodel, and it's going to keep all the states from everything else besides the fairing. So a way to manage different configurations that are here. You could also use it for building different sets of radiation couplings. You know, I want to do a deployment analysis, so let me do my stowed case, rad case, and then rebuild with my deployed rad case, for example. All right, then after here, there's a post-build solution. So after the build, this TD heater is what's going to take all of the steady-state heaters and determine what they're supposed to do, whether they're the hold them as heater nodes, apply a certain amount of power. Then we have a call to steady. Then we have the TD release heaters for transient. You can see here the dollar signs for the comments after it. If an F doesn't appear over here, then it defaults to an M-type statement. That's why I can have this dollar sign here. So if it doesn't have a definition, then it's implied to be an M. Then we call the transient. Heater output summary. This is the heater information at the end of the output file. And then any logic that I might have after the solution goes here. Here's my control data 0, absolute 0. This defines what temperature units I'm in. So this says C and not K. Sigma, this is watts per inch squared, Kelvin to the fourth. Maximum number of loops for steady state, maximum number of loops for transient. Initial time, end time, time to be used for steady state, atmospheric pressure, DRLXCA, RLXCA, these are the relaxation criteria. This essentially is what is the maximum allowable temperature difference between two iterations before I consider the solution converged. MATMAT matrix method, this is how to solve. This XLIM and ITER-XT deal with some of the extrapolation capabilities. EBAL, SA, and NA, this is the energy balance for the system, energy balance at a nodal level. ITER-UT is how often to go to the output calls if you set this to something other than that. IT hold is really an old function, but basically you could say once one submodel is converged, I want you to stay dormant and not do anything for IT hold iterations before you reactivate. It was a way when you were dealing with iterative solutions and parts of it had converged to not have to spend as much time there. Output interval, maximum allowable temperature change per time step. The time to use, D time I, if it's 0, it'll do automatic time stepping. Maximum and minimum, CSG factor, and so on and so forth. This is all, I think, information for Fluent type stuff below here. Although sparse G is one. Sparse G is a sparsification approach where they look to see if the linearized conductor is less than that fraction of the total conductances for each node, then it will set it to 0 for much of the solution. And once it's converged, it will then reactivate it and see if it's good. So it's a way of taking very small terms and trying to make them 0 to make the solution faster. Rest of this is for the solver. We might talk about that in a little bit. And then here you see the insert lines I was talking about. One thing to note here, you see this K_in. This is a newer format. What it is it's a binary format that the RAD-Ks are stored in. The RAD-Ks themselves are actually in the K file. So if you wanted to look at the RAD-Ks, you'd look at the K file. But the K_in file loads considerably faster because it's already in a format that Cinda can process and store back into how it needs it without having to read through the text and then figure out how to store it. So, and then here is the heat rate arrays. So this will be array data. And then the heat rate load, this would be variables 1 or variables 2 data to load the information from the HRA. So let's then open up and see what's in the CC file. All right. So CC file actually does contain quite a bit of useful information if you want to look at it. It's got the units. It's got the list of the thermophysical property and optical property databases that were used. It's got the drawing file name it came from. And it's got all of the symbols, what their values are, what they were input, and then any sort of a comment here. So you can see all the symbols that were used. It's got aliases that were defined. And then it jumps into the actual logic or the code that's needed for Cinda. So this is all the register data. An INT in front of it indicates that this is an integer as opposed to a floating point. You can see the comments out there beside it. So there are all the things. If you put in a user comment, it's here. If you didn't, then it's not there. For all the heaters that you create, there will be some variables that are automatically done for you. So there's an OT, that's the on time. There's a PO, that's the power available. There's a power used. HY is the heater capacity. HTN, I think that's the number of on-off points. So this is why it can be useful to put something that makes sense for the heater name so that if you reference any of these other symbols that are automatically created, you can get it. So what the on-off temperatures are, the proportional, damping factor, total power, and so on and so forth. And then here is the header node data for the boom submodel. We'll go through this in detail in a little bit, but this is node number, initial temperature, and capacitance. If this is a -1 here, then that means that it's an arithmetic node. If this term is negative, it's either a boundary node or a heater node. They basically do the same thing. The exception is that a heater node will allow you to call some functions that retrieve the amount of heat needed to be put into or taken out of the node to hold it at temperature. So if this is negative and this is negative, it's heater. If this is negative and this is positive, then it's a boundary. Here's conductor data. So we've got the boom. And here you can see I had a comment in there, dish to the boom. So here's a place where the comment was output to the output file. And I might be able to use this for documentation if I were able to extract it. The negative sign here indicates that this is a radiative conductance. A positive sign here means that it's a linear conductance. So from linear conductor from boom submodel node 1001 to boom submodel 1002 with a conductance value of 0.288, blah, blah, blah. So you can scroll down here, another place where it's there. Node data for component A, variable 0, variables 1. Here's another comment, the heat load dissipation on component A, 66 watts. And here's a place where you can see that I have output it as an expression. If I had output this not as an expression, then it would take whatever the values are of this and put them in. So then I wouldn't be able to change it by changing the symbol. It would have to be something where I'd have to do it manually somehow instead. It almost always does this additive to it. One of the reasons for that is at the beginning of variable 0, all Q values are assigned to 0. They're zeroed out. So that it's sent to 0, comes through and adds this value to 0, and it's good. And so the next one that would get added to what's there. So if I have a heat load and then a heater after it, it sums up onto it because it knows it's zeroing it out every time. One thing to be cautious of, if you have to go to Esetan, which is very similar to this, Esetan does not zero out the Qs before it starts its iteration. And so if this were put into Esetan without being more careful, this value would keep going up and up and up as each iteration passed because it would keep adding to it because it never was reset to 0. So just a little tip to be aware of. So again, component B, heat loads for component B, component C, component D. So you can see that this is all starting to look pretty good or pretty familiar. Here's a place where the contactor is listed. So you can see what the contact value is that's in there. Keep going down. Say again? Ooh, I don't know if I can. You think scrolling will do it? Nah, Control Shift and Alt aren't doing anything. So, yeah. All right. Here was the place where I put in my own user logic. You can see the comment here. This is the shadow entry, less than 0. Here we're using the modulus of the time, so Cinda variable, so on and so forth. This is the logic for a heater. So the available power, if the solution is less than 1, this means it's steady state. So this logic would be executed for steady state. The logic down here would be executed for transient. So here it sets the on temperature, the off temperature, what the sensing temperature is supposed to be. So here you can see component H, temperature of node 1041. That's what's going to be used for sensing. It applies this damped proportional factor to it. And then once it's figured out what the proportional amount of power is, it distributes that to the nodes that are associated with the heat load. So this is also Cinda logic where I'm saying the Q value assigned to these nodes. Slightly different down here. I just need to see if I'm above or below a temperature. I don't have to come up with a proportional amount. It will still be full power or not. Otherwise, it sets the power to 0. Okay? So the logic is really just a bunch of these blocks. We'll get all the way down to the end. And you can see these are all the different submodels with all the conductances in it. All right. Okay, so header node data for solar panels, and now header output calls for solar panels. This is where I put my own user logic. So this spell off directive says don't check spelling in here. That lets me use some of these functions that I've developed and put in here. So these are some user functions. So I'm outputting the temperature of component A, the 3 for B, the minimum and the maximum of the submodel for component C, the range of D from 1,000 to 19999. This should be 2,000 to 29999, 3,000. So this is the file that gets written. I open up this file specifier in operations, or somewhere I open it. I forget exactly where. It writes to that file using this format. So this is basically mostly raw Fortran with the M-type statements being allowed to convert this T1001 to wherever that location for the temperature of that node is stored. And here you can see in column C, or column B. In column 6, I have the continuation lines. Here are subroutine data. So this is additional subroutines that Cinda has done. So when we saw that call to TD heater, TD release, this is logic that Thermal Desktop adds automatically, TDHTOT. So based on the heaters that you have, this logic will be written out by Thermal Desktop. Heater reset, pre-build logic, post-build logic, base plot, and then these are some of the functions. This was the subroutine maximum, subroutine minimum, submodel maximum, submodel minimum. These are user functions that I've developed to do a little bit more than what Cinda does. So these are extending the capability of Cinda with user-defined functions. Then we get down here to the end. And when it gets to this point, it's going to return back to the input file and then go read through the k-ins. So we'll take a look at the k file so you can see what that looks like. We're not going to do the k-in. So k file, similarly, header conductor data, sample rad k is what I called it. This p-stop directive says don't echo all of the lines that come here to the preprocessor. Again, similar information here. One other thing that's added, though, that's very useful, you've got the optical properties and what the values are. So if you need to see why two cases were different, you can check and see if the optical properties were different between them. We found something that was a surprise on Roman that turned out one of the emissivities was 0.5 and another was 0.01. So that ended up explaining what it was. And then here are all the rad Ks with the format of the conductor number. Again, the negative sign telling you it's a rad K. Node 1, node 2, and the area times the E times the Bij. Really, you know it better as the area times the E times the Bij divided by the scale factor, what it winds up being. And then out here is the Bij and Bji. So for space, there is no return. There's no Bji. It's only a Bij. But if you look down further, when you get past all of the space nodes, or all the space couplings, now you see both the Bij and the Bji as a comment to this. So if you really were interested in how this rad K got done, you could take these numbers, find out the number of rays that were fired for these two, get the errors, and then do the math, and you should come up with exactly this number. So you do have the full traceability knowing how those numbers get used. All right, down at the end of the file, once it's done with all of the rad Ks, there's some comments here. This is where it tells you what the area is that's associated with that node, how many rays were fired, what the emissivity is with it, the Bij sum, the Bij that it has to itself, the Bij to inactive surfaces, and then the weighted error that was used for that particular Bij. So you have all that information for the ones that met a particular threshold here. I think there are ways to change this if you need to. But what you're generally looking for is, for the most part, that these numbers tend to be high. If you see something really low, you might try to understand. So here, this is probably looking up at a blocker surface, since I see the Bij to inactive is very high, and likewise here. So again, some useful information in there. How many calculation nodes, how many rad Ks were output, how many were filtered, and so on and so forth. So some useful information to check in the rad K file. Once it would be done with that, it would then return back and it will come to the HRA file. So let's open that up. Okay, so here, Cinda Fluent, solar albedo and planet, time units, data array units. Here are the vectors that we discussed earlier. So this is where the sun is, this is where the planet is. This is the orbit radius divided by the planet radius. So this number is usually close to 1. The time, the mean anomaly, the true anomaly, whether you're in sun or eclipse. Down here you've got, I think, the velocity vector, some other information. Again, more information about all the symbols. And then this is all commented out because I think it uses the HRA bin files now. But this information is here for you to see the average heating rates for all of the nodes. And then you have the storage space for things, the time array, and then the arrays for each of the nodes from a transient point of view. So much of this is now commented out because they use a bin binary file for loading it faster. And then lastly, there's the character array. This is used in conjunction with the steady state data. And so this is a combination of submodels and node numbers. And so the order that things appear here is the same sequence order that you'll find for the steady state numbers. So once it would be done with that, it would go to the load file, so the HRL. Okay, so this is then going to call the load queue sample HR blah, blah, blah. This is the subroutine that they define, uses the binary reader instead, and so this is the logic that it has for it. Again, deep Fortran, I haven't looked at this yet to fully understand it, but this is how they approach things now. So then it would be done. It would have read all the data in, and it would then go through the pre-processing. So that's a Cinda model. That's really what is being executed and solved for the temperatures. All right, so we talked about the entry point where everything starts. So the solutions run through variable 0 is where you process the time-dependent logic. This is one time through this per time step. Variables 1 processes temperature-dependent logic. This would be multiple passes through, each iteration in steady state, or one time through in transient, unless you tell it, I want you to go through every time. So the assumption in transient is that things aren't going to change much between iterations, between time steps, whereas in steady state, things may change rapidly. So you have to tell it that you want it to go through variables 1 multiple times in transient if you want it to do that. Once it's gone through variables 1, it internally solves for the temperatures. If it's converged, it goes to variables 2. If it's not converged, it will continue to go back through. Once it's converged or it hits the maximum number of loops, it then goes to variables 2. And then it will exit out. If you're transient, you go to the next time step and start back at variables 1. If it's steady state or transient, you complete the last time step, then you go back to operations. And at the start of the solution, every output increments, so every 300 seconds if I told it that, and before returning to operations, it will go through output calls. So this is how frequently you can output it, and basically will break the solution. Not break the solution. It will exit from solving, go output the stuff that you've told it to, and then return back. It will automatically adjust time steps so that you land on it. So if you're cruising along at 30 seconds, 30 seconds, 30 seconds, and you wanted to hit it at 45, it will stop. It'll use a smaller time step to make sure it lands on the next time step increment in order to get there. So submodels, I assume you're familiar with submodels, but in case you're not, it's a way of logically grouping things together. The names are limited to 32 characters. They can include alphanumerics and an underscore, but you can't begin it with an underscore. It basically allows you to do two things. Number one, not have to say, you get node range 1,000, you get node range 2,000, you get node range 3,000. You can say use whatever nodes you want, as long as your submodel names are different. We have a unique identifier to keep them separate. The other thing it does is it does allow you to tailor how accurately you need to solve each submodel. So I could say, this submodel, I'm not worried about millikelvin accuracy, solve it to 0.01. This one I really care about getting it accurate and being stable, so you solve a little bit more. So it's a way that you can control both the solution accuracy, throughout certain parts of it, as well as just logically grouping things together. We talked about that build command. So you can have multiple build statements in there. It's basically when you go solve, it's going to solve for whatever the current build configuration is. So this one I could build submodel A, B, and C, and D, and this other one I could rebuild it and say build submodel A, C, and D. So just a different way of solving for what you need to solve for, what's included in the solution that you care about. Insert and include files, we talked about that. P-stop and P-start, this basically says don't continue echoing stuff to the preprocessor. The file for the RAD case could be very large. It can make your preprocessor output file very, very big. Don't really need it. F-start and F-stop, these basically say, hey, from here on out, consider everything an F-type statement. So it overrides the default of M. And then default model. So if you're in a header variables 1, you've implied the submodel. But if you're in operations and you say, tell me the temperature of node 1000, it doesn't know what submodel you're talking about. So this lets you define the submodel if you don't explicitly put it in there. All right, so first header is the options data. We talked about that. Usually have your output file, your save file, whether you're solving in double precision. I think this is default now. It used to be that you couldn't have more than 6 digits for node numbers or RADK numbers. I think it's now 8 or probably even more than that. Mix array is something that you might see from time to time. This allows you to have both integer and real numbers in an array. And when we get to the data structures, you'll see why that's important. We talked a little bit about the submodel. The basic format is the node number, the initial temperature, the capacitance. Based on those values being positive or negative, it defines whether it's a diffusion node, a massless arithmetic node, boundary, or heater. The capacitance we define as the mass on the specific heat. Temperatures, you get an initial temperature, but these are what are going to be solved by Cinda. You got to have one boundary node. There are some special temperature dependence or multiple node things. Those will be covered later, but I think we skipped those in this. But here you can see the 4 different types of nodes based on the variables that are put in. Conductance data, similar format. G number here, greater than 0, it's linear. Less than 0, it's radiative. If you specified sigma, then you multiply sigma times G. So usually G is in terms of area. You could also say sigma is equal to 1 and put your G's in terms of watts per Kelvin to the 4th. Just got to make sure it's consistent, but it's going to use a T to the 4th relationship. If you don't specify the full submodel name for Ni and Nj, you just put numbers here, then it's going to make the assumption that the submodel assigned to those is the same submodel that you're defining the conductor data. Cinda nowadays writes it out explicitly. It's better practice to write it out explicitly because it doesn't imply anything. So it's just a better practice to do that. Conductances are used to satisfy the energy balances. Based on these Qs, you're essentially balancing all of the Qs coming in, going out, what's generated, and what's stored. Again, we'll talk about the other types of conductors if anybody really wants to. One of the things that's kind of funky, yes, you can't have a negative conductor. We saw that earlier. But if you see a negative sign on one of the node numbers, what that indicates is it's a linear, or it's a one-way conductor. That doesn't mean direction of heat flow. It's more for a fluid and a wall temperature. The wall shouldn't be heating up the fluid or cooling down the fluid. The fluid is at some free stream temperature. So the wall gets heat from the fluid, but the fluid doesn't get heat from the wall. So it's a one-directional. They talk about it differently now. They don't call them one-way conductors anymore, but that's what they were referred to a long, long time ago. So if you see a negative sign there, it's basically saying that node 1001 knows about and can be influenced by fluid.1, but fluid.1 doesn't know about and can't be influenced by node 101. So, all right, conductance terms, pretty basic. Source data, if you see this little thing here, this is legacy information. This is old. If you get a model from 20 years ago, you might need to see this, but probably not. In this case, I would not use source data. I would use the variable 0, variables 1 to insert the heat. But you could put it in source data and apply a 70-watt load on node 101. Control data, there's a variety of different control things for what makes the solution behave the way it does. Stefan-Boltzmann constant, we should all be familiar with that, absolute 0, maximum number of loops. We talked about each of these, I think, during there, except for Fabebula. Fabebula is a forward-back nodal energy balance that only is applicable for transient. So I tend to avoid using this one. It often just makes the solution not converge and not really make any progress either. So, all right, header operations data. That's where everything begins. There's a build all. It's going to build everything. Otherwise, we build submodel or the model name and then all the submodels. Open up any files we need. Call steady state or std SDL, forward, back, or transient, and write any output files that we need to and close it up. Some of the things that you might find in output calls, tprint, outputs all of the temperatures for all the nodes for the submodel name that you have here. You can say all, that would do basically tprint for all of the submodels. Qprint outputs the heat loads, cprint capacitances, gprint Conductances, if you output a G-print, can get very large. HNQ-PNT, don't use that. It's basically outputting the heater node Q there, but unless they've changed it, it doesn't output a header for you to know what submodel that's in. So you just get the node numbers, but not the submodel. So if you're going to use that and you want to know that, you call HNQ-Cal and then do a Q-print. So HNQ-Cal calculates the heat that you need to hold the boundary temperature, either into it or out of it, and then stores it in the Q variable such that when you do a Q-print, you can see, okay, my boundary node needed 30 watts taken out of it as a heater or 30 watts put into it in order to hold it at temperature. Node map allows you to look at a heat flow map at a nodal level. Can get very large. QMap basically calls node map for all the nodes. That can get huge. Submap can be useful. You can look at submodels, submodel to submodel heat flows. So this is all stuff that if you're trying to look at the output files rather than trying to process it in desktop, you could use this to do it. The output to the binary files, there's a call save, and then put the arguments, and this can be a combination of T's, Q's, G's, C's, N's is register, or I forget what N's is. I have to look at that. Control constants, there we go. And then registers. If you have called use CSR, then it would go to a CSR folder rather than a save file. All right, so let's go through a single model example. Basic conduction, 10 watts going in. We got our distances here. Closed form solution would tell us what the temperatures need to be. So the green nodes would be at 330, 320, 310, 300. The red nodes would be 325, 315, 305. And the blue nodes are 330K to the left, 300K to the right. So the finite difference, we're going to add in this half conductance here, and then go from 2 to 3, and 3 to 4, and 4 to 5 with the half conductance. Edge nodes, we have it, and then the conductances for finite elements. So this is what the SINDA would look like. There's the options data, absolute, 0, header node data. Here's my boundary node at the end with a negative sign. Here's the conductance values, call the steady state, and then call tprint. To execute this, I would run SINDA win. So this is, outside of desktop, you're building this. So you go start, programs, SINDA Fluent, run SINDA Fluent. You get this up, select browse to select your file, and hit run SINDA Fluent. It's going to run through and give you the compile, the link, any flags it gets, and go on. So when we look at the output from that first Centroid base file, we see here, okay, these are not a solution. That's an initial temperature. Well, yeah, this is initial time of 0. There are no loops. We haven't tried to solve anything yet. So this is the initial condition. This is the call to output calls before you've done the solution. Final solution. Took us 2 loops to converge. And lo and behold, we got what we expected. 330, 325, 315, 305, and then the boundary at 300. So now if we look at the bar a little longer with an edge node formulation, so we're going with the green dots here, see what the conductance looks like. We're going to put half of the load in here, half of the load in here. We're going to hold these two as boundaries, so there are 2 nodes there, 300 and 300. And the results, well, we doubled the length, so the delta T goes up. So now it's 360, 340, 320, exactly what we expect. What about that finite elements formulation with that negative conductance? We had this funky minus 1.66667. Well, we get the exact same temperature solution, 360, 340, 320, 360, 340, 320. The 300's there. So yeah, it's got a negative one, but if we look at the energy balance into node 2, we'd expect it to be 5 watts. And if we go through all the math, lo and behold, yes, it does come out to be 5. So from an energy balance into this, looking at everything, we're okay. Doesn't work for, well, what's the heat from 1 to 2? But from an energy balance point of view, it holds with physics, makes sense. So you still can check energy balance, just not at an individual conductor level. And I welcome all of you to take the values here and plug it into Thermal Desktop, and I would expect you to get the exact same numbers here, because otherwise I wouldn't have known how to get that. So this came out of me trying as a Cinda deck, and I think Shinichi-san even tried it and got the same thing. So it seems to work in all time zones. All right, so moving into intermediate Cinda, we're going to skip some of these other things that are here, but we'll talk a bit about logic blocks and basic Fortran. So logic blocks give you access through Fortran to many variables that are implicitly defined by the Cinda constructs that you have. So when you make node 101, you automatically get a T101 that represents the temperature of that. You get a Q101 that represents the heat load applied to it. If it's a non-arithmetic node or a non-boundary node or non-heater node, you'll get a C101, which is the capacitance for it. When I've defined conductor number 101, I get a G101. If I happen to define an XK or a K, I could get some user data. I could do array data. There's an array number 5 would be A5. NA6 would be an integer array. And then the UCA is a character array. So depending on some of the data blocks that you had, you would get different variables that are created with this. You also have a variety of explicitly defined control variables from Cinda. So the relaxation criteria, the D time I. There's also an I test through N test, which are integer values that you can use as a temporary storage space. There's also A test through H test, O test through Z test, which are real variables. So if you just needed a loop, do I test equals 1 to 100. You have your explicitly defined Cinda global variables. So register data, user data, global. You have any local Fortran variables you've defined, and then you have all of the Cinda functions that are included in the library that you can look up in the manual for doing things. Colmore and Ring doesn't tend to use nearly as many of the functions as they used to because it was just easier to write the code for heaters to do it rather than reference a heater routine. So they tend to just use the logic that they write out from Thermal Desktop rather than functions in the Cinda library at this point for most of the things that are exported. So header variable 0, 1, and 2. Again, interpolation of environmental loads, constant power dissipations, time-varying conductances, variable 0, heater simulation, power dissipations that depend on temperature, such as a heater cycling on and off, conductance values that may be temperature dependent, capacitances that are temperature dependent, that would go in variables 1, logic for what to do afterwards, and then logic for writing out user-specific or sending the results through T-prints, Q-prints, that kind of stuff. Those are the different places you would put it in the deck. So basic Fortran helps to understand this because Cinda was written a long time ago. Fortran 77 is still a very good number crunching language, so it's still used. I think actually now you shouldn't go beyond column 132, but 72 is what it was when I was in school. Characters in column 6 is continuation, 1 through 5 is line numbers. Data types should be declared, so you want to tell it that it's an integer and not an integer, but just an integer. So if you do a *8, that makes it 64-bit, otherwise it'd be 32-bit by default. Real *8 for 64-bit. Characters would be string values. Dimension to make an array. You can't dynamically allocate space though, so you have to know how big your array needs to be if you're using an actual Fortran array. Go-to commands are available. I would advise not using them. Makes for a really difficult spaghetti code to follow where go to 321 and well, where's that, and so on and so forth. So better to use structured code if you can. Conditional statements, if a condition, then, else if condition 2, then, else, end if. Loop statements or do I test equals 1, 10. You could do an increment of 2, 10, 2 to increment it in groups of 2. End it with an end do. There's a while. And then these are the different types of conditions that you could have. Not equal to, greater than or equal to, less than or equal to. And then logical ands, logical ors. So you can combine these things to come up with the logic that you want to define how the code should flow. Basic input and output. You open a file, you specify the unit specifier, you specify the file name, you specify the status is unknown generally. If you're opening your own file, it's a good idea to do a .. slash or .. backslash, because when Cinda solves, it actually creates its own directory and solves in there. So if you want it in the same directory where your input file is, you have to go back up to the parent. That's why this .. is here. So this would have been a file to output the heater duty cycle. You can read things, specify the file specifier and the format line, and then the variables that you want to write out. Write is very similar. So if you put the M-type statement in this, it would convert this submodel.t100 to the appropriate index location. Format specifiers tell it how to write something out. So F is a decimal notation. In this case, it would be 10 characters wide, 6 after the decimal place. E is scientific notation, 10 characters wide, 4 after the decimal place. I is integer notation, 3 is, or X is spaces, A is a string. Once you are done with a file, after you've opened it, you want to close it. So here we open a file, we write the temperature for node 101, we write the temperature for Q101, but note that I started this with an F type and then continued it with an M type afterwards, had the comment there, and so the Fortran or the logic would be written correctly to deal with this. So you can't split an F type and an M type statement across lines if you need to do that. Here's the format specifier, and then close it when we're done with it. All right, so that takes us to advanced Cinda. I think we have a break right before then. How are we doing on time? Yes. Are we ahead? We're about on time? We're right on time. It's time to break. Time to break. Excellent.